All right, so for this video, I'm going to go over the rotational dynamics worksheet, at least the first couple, on moment of inertia. YouTube makes me, kind of limits my time on these videos, and so I have to make them short and kind of piece them together. And so let me just pull up my screen share here, and we'll look at the first maybe 4 or 5. So let's just take a look at number 1. So keep in mind, a moment of inertia depends on 2 different things. It depends on the object itself. So is it a hoop? Is it a disc? Is it a cylinder? Is it a rod? It depends on what the object is, and it also depends on how that object is rotating. An object rotating, say, about its axis like this, it's kind of hard to see, but about its axis like that, is going to be different than the same object rotating about one end like this. And so we have to know how it's rotating. And so if I go, actually, I'll just leave my screen up like this and refer back to the page. All right, so for number 1, what is the moment of inertia? And keep something else in mind, which is that AP isn't going to expect you to memorize these formulas. They're going to give you a lot of the common moments of inertia on your AP exam sheet. And anyone that wouldn't be on your exam sheet, they would give it to you in the problem itself. It's not something you have to memorize. And so the moment of inertia for a solid cylinder is going to be 1/2 mass times the radius squared. Keep in mind the radius should be converted between centimeters to meters, and our mass is 3 kilograms. And so we plug all that into here, and we'll get some value. I have to remember what this one is off the top of my head. It's 0.0864 kilograms times meters squared. There's no special unit for it. It's just the unit for mass times the unit of length. So that's kilograms times meters squared. All right. And then it wants to know, what is its angular velocity given its period? Well, remember, we can say the angular velocity, omega, is equal to the tangential velocity over the radius. And the tangential velocity is just 2 pi r over the radius, or I'm sorry, not over the radius, over the period. We still have an r in the denominator, so I'll put that in there. You can see the r's cancel, and our formula is then going to be 2 pi over the period. This is the formula for the angular velocity given the period. And so we can plug in the period of 15 seconds, plug in pi, and so this would be 2 times about 3.14 all over the period of 15 seconds. Plug that in, and then whatever value you get, if I remember correctly, it's 0.14 or 0.41. The units are radians per second. It's angular velocity. All right, so let's take a look at number 2 then. Number 2 says, what is the moment of inertia of a 0.5 kilogram rod that is a certain length, in this case 40 centimeters? Well, for this, our moment of inertia, the formula for a rod is going to be I is equal to, and then it's also rotating about its center too. It doesn't say that in the problem, and it should, because it's going to be a different moment of inertia depending on how it's rotating. And so in this case, if it's rotating about its center, the moment of inertia is going to be 1/12 mass times length squared. Our length is 0.4 meters. Our mass is 0.5 kilograms. Plug that into your formula, you'll get some value. Always remember the units. The units are kilograms times meters squared. And that's your moment of inertia. All right. So the next one is a little more complicated. It says we have a 3 kilogram uniform solid cylinder with a radius of 6 centimeters and a length of 14 centimeters. What is the moment of inertia of a cylinder spinning around a central diameter? And so in this case, our moment of inertia is going to be 1/4 times mass times the radius squared plus 1/12 times the mass times the length squared. And so when you go ahead and plug that in, well, we have a radius of 0.06 meters. We have a length of 0.14 meters. Plug all that in, and you'll get your moment of inertia. And then it wants to know if it has an angular velocity of 2.5 radians per second, what is its speed? So we can just use the same formula that relates speed to angular velocity as before. We can say that omega is equal to V over R, and therefore V is just equal to omega times R. Omega is at 2.5 radians per second. R is the 0.06 meters. When you multiply those out, remember radians isn't a unit, and so you'll be left with something in meters per second, and that'll be your speed. Okay, so number 4. A 35 kilogram door is rotating about its hinges. If the door is 1.2 meters wide, what is the moment of inertia of the door? Hint, treat the door like hundreds of rods stacked on top of each other. I don't know if I really like that hint because I feel like it almost throws me off a little bit. But what I do know is this. I do know what the formula for the moment of inertia is of one rod rotating about its end. And I know that that formula is I is equal to 1/3 mass times length squared. And so if that's one rod, well, then what about all the other rods? Why is it telling us that we need to add them all up? Well, that just means that we're going to be using the mass of all of them, right? The length still remains the same. So let me just draw a little picture here. The length still remains the same. And the radius is negligible. So really all we have to take into account is the total mass, which is 35 kilograms. And so when we plug that into our formula, it's just 1/3 times 35 times the length squared. Well, what is the length? Well, the door is 1.2 meters wide. So this length right here is 1.2 meters. And so that's 1.2 squared. Multiply that out, and that's your moment of inertia. All right, number 5, I think I'll stop with this one. It says, what happens to a spinning object when A, the moment of inertia of the object increases, or B, when the moment of inertia of the object decreases? And so for this one, it's a good segue because it's almost an intuitive answer, but it's a good segue into what we'll get to eventually, which is something called angular momentum. And just to help illustrate the problem, I'm going to write the formula for angular momentum. So keep in mind, when we're doing rotational things, instead of writing mass, we write the moment of inertia. And instead of writing velocity, we write angular velocity. So remember, our regular momentum is just mass times velocity, or angular momentum is represented with an L, and that's equal to our moment of inertia times our velocity. So it's again, the moment of inertia takes the place of our mass. Why do I write this up here? We don't need to know this formula to answer this question. Just think of a figure skater, right? If a figure skater has his or her hands stretched out like that, they're going to spin, their spin is going to slow down. So what's happening? Well, they're increasing their moment of inertia by taking that mass, their mass, and putting out their arms like that. They're now distributing their mass in a different way. And so therefore, the moment of inertia would increase, and therefore the velocity would decrease. And the reason I put this formula up here is because we say that angular momentum is conserved. It's just like a linear momentum. It's conserved. It's a really important property of momentum and angular momentum. And if this is conserved, that means that as our moment of inertia, these races here, that means that as our moment of inertia goes up, our angular velocity must go down. Or another way of saying that is if our moment of inertia decreases, our angular velocity increases. So the figure skater analogy, as the figure skater brings his or her arms in, they decrease their moment of inertia. And because our angular momentum has to stay constant, that means that our angular velocity must increase. So as they bring in their arms, they start spinning faster and faster.